Have you ever really thought about the materials all around us? I mean, from a simple paperclip to a massive skyscraper, everything has a hidden story about how it handles pressure. In this explainer, we're going to learn how to read that story, and we'll do it using one of the most important graphs in all of engineering.
It all kicks off with a question you've probably wondered about. Why is it that you can stretch a rubber band, let it go, and it snaps right back? But if you bend a paperclip just a little too far, it stays bent forever. The answer to that simple question, well, that's where we find the secret life of materials.
So, to understand this secret life, we first have to learn the language that materials speak, and that language is really built on just two key ideas: stress and strain. Okay, first up is stress. Imagine you're in a tug-of-war, pulling on a rope. The force you're yanking with creates this internal fight inside the rope. That internal force, spread out over the area of the rope, that's what we call stress. It's the material basically saying, hey, I'm being pulled apart here.
Now, if stress is the action, then strain is the reaction. It's really just a way to measure how much the material actually changes its shape. How much it stretches or squashes or bends away from its original form when all that stress is being applied.
And you can apply stress in two basic ways. You've got a tensile load, which is a pulling force that stretches things out, and then you've got a compressive load, which is a squashing force that squeezes it. Each one reveals something totally different about what a material is made of.
All right, now that we've got the lingo down, we can actually read the material's story. And that story is told by something called the stress-strain curve. Think of it like a complete biography of a material under pressure, from birth to, well, the breaking point.
And here it is. It looks simple, right? The vertical axis, going up, that shows stress, how much force we're applying. And the horizontal axis, going across, shows strain, how much the material is deforming. As we trace this line, we're literally watching a material's entire life unfold.
The story always starts here, in the elastic region. This first part, this straight line, this is the rubber band phase. As we add stress, the material stretches, but if we were to let go, it would snap right back to its original shape. Totally fine. It's perfectly elastic. Right at the end of this perfectly behaved region, we hit a key moment, the proportional limit. Up until this point, stress and strain have had this perfect relationship. You double the stress, you get exactly double the strain. It's beautifully predictable, a principle known as Hooke's law. But what happens if we keep pushing it? We reach the yield point. And this is the point of no return. Once a material is stressed beyond this spot, the damage is permanent. It will never go back to its original shape. This is exactly what happens when you bend a paperclip. You've pushed it past its yield point.
As we keep applying more and more stress, we climb all the way to the very top of the curve. This peak is called the ultimate strength point. This is the absolute maximum stress the material can possibly handle. It's the material's moment of glory, you could say, holding on with everything it's got before it starts to fail.
And finally, we reach the end of the story, the fracture point. After hitting its peak strength, the material actually starts to get weaker, and then, snap, it breaks. The story is over. The material has completely failed.
Okay, so we've just read this pretty dramatic story of a material's struggle and failure, all on a simple graph. But why is this so important? Well, because this curve isn't just some abstract thing for a textbook. It is quite literally the blueprint for building our entire modern world.
Seriously, engineers use this curve for everything. They'll pick a material for a bridge that stays way inside its elastic region, so it can flex under traffic but never, ever bend permanently. But for a car's crumple zone, they actually want it to go past its yield point to absorb the energy of a crash and keep you safe. From the aluminum in your soda can to the alloys in a spaceship, this curve dictates what's possible.
You see, every single material tells its own unique story of strength, of giving in, and of eventually breaking. So the next time you stretch a rubber band, or maybe see construction on a new building, just take a second. What kind of story do you think the objects around you are telling?